Alright, so welcome to last week of the quarter. So first off, as I mentioned last week and the week before, today's class is going to be short. So I have a meeting I have to go to at 1 o'clock. So I posted yesterday an announcement on Canvas with a suggestion for how to spend the extra 50 minutes that I won't be with you today. So there's a link to a video. This is actually a lecture from last winter where I covered some of the topics that that we were going to be going over today. Oh, thank you. I've definitely enjoyed teaching this class. I appreciate that. So if you click through on this video, I put in some suggested times. Basically start from about the 19.5-minute mark through to the end, and it'll cover three topics. BNF, which is a way of representing syntax of a language, and in particular it's a way that can be fairly directly turned into code that can be used to analyze input and parse it for syntax. And then state machines, which is something we talk about in Engineering 250, but looking at state machines and how they apply to language recognition, and then wrapping up with Turing machines, which is where I want to start from on Wednesday. Thanks for the comments. I appreciate hearing those. Yeah, I think this is a cool class, and it's definitely stuff that you'll encounter again at a university. You'll do a whole course focusing on sort of the grammar aspects, language, automata theory, things like that. And a lot of the other themes will come up again and again, so it's a good intro to stuff you'll be seeing later on. So I'd like you to watch this video. It's about 50 minutes worth of lecture. You don't have to do it, at 1 o'clock today, but sometime before Wednesday, so that hopefully we can talk about it on Wednesday and continue from there. Wednesday we'll mainly talk about Turing machines, and two particular aspects we'll be working towards. One is the halting problem, and the other is looking at deterministic versus non-deterministic Turing machines, which will take us into something called NP completeness, which is another one of these famous open problems in computation theory, and kind of a good ending point for the course. And then Friday we'll just do review, whatever questions are lingering, whatever things we haven't touched on yet, and that'll do it for the course. So your final exam is a week from today. It's at 12 o'clock. So not 12:30. So a week from today, 12 o'clock, and it'll be about an hour and 50 minutes. And we'll talk about details of the final on Friday. And you can comment on the video in class, definitely. Yeah, I'd love to have a discussion about it. We can do that on Wednesday. And I'll run through the topics really quickly, assuming that people have already seen them. But we'll have a conversation on Wednesday about those pieces of the course. So let me talk about the homework. So two things about the homework. One, I posted some homework questions for you to work on for the material that we're doing right now, which is languages and automata theory. I'm not going to collect that homework. I'm not going to grade it, okay, because there's just not enough time to do that and get it back to you. But I would like you to try the homework, right, as we're going through the material, and ask questions about it. And we'll see how far we get through this stuff on Wednesday. But that homework that's posted does not have to be turned in. Let me talk about the prior homework, which I graded and posted on Canvas, and that was related to graph theory. So let's just do a quick run through on the questions I looked at there. So let me pull up a copy of this. Hold on a sec. I think this is probably the one that you did. So I graded questions 3, 4, 5, 6, and 7 from here. Because if you can do those, you probably understand the material from questions 2 and 1. So question 3 was just drawing an undirected graph for the given adjacency matrix, and you know, however you decide to label these, you end up with a graph that looks similar. So 0, 1, 0, 1, 0, 1, 0, 1, 0, and we're told it's undirected. So if we just label these A, B, C, right, and I can put these vertices anywhere I want. This basically tells us where we have edges. So there's an edge between A and B. That's what this tells us. It's also what that tells us. There's an edge between B and A and B and C. And there's an edge between C and B, and that's your whole graph. So it's really just 3 dots connected. All right, so that's question 3. Question 4 was drawing a directed graph, and so I don't think I need to do that one. Everybody, I believe, got it right. And this was the one that we started to do in class, and I said I wasn't going to finish it. So there's a vertex from A to A to B, and A to C. There's a vertex from B to C, and that's the only vertex coming out of B. C has a vertex to A, and also a loop, C going to C, and then D has vertices going to A, B, and C. So A, B, and C, and so there's your graph. Let's see. All right, so that's question 4. Question 5 was looking at isomorphism of graphs, and most people discovered that these were isomorphic. You can count, you know, degrees of vertices and convince yourself that they could be isomorphic. But to actually find the isomorphism means to find a mapping, and in this case, our first graph had vertices A, B, C. Our second graph had vertices X, Y, Z. And an isomorphism means, you know, some kind of mapping from this set of vertices to that set of vertices, and it has to be a one-to-one onto mapping. And so you could say, you know, something like A goes to X, B goes to Z, C goes to Y, or, you know, f of A equals X if you're using F for your mapping. You can just show what F takes each of these points to, and assert that that's an isomorphism. The PDF is not obstructing what I'm writing yet. It will be shortly, but I only wrote as far as that. So that's how you answer an isomorphism question definitively. If they're isomorphic, you actually find a mapping. If they're not isomorphic, then the graph. Oh, you're right. My bad. If they're not isomorphic, then you can find, you know, a mismatch in the set of degrees, in degrees or out degrees, and so on and so forth. Yeah, that was the graph from the previous one. Sorry, that was obscured. But everybody seemed to get that. A few people missed one edge here or there. I think that's just typo. All right. So question 6, yeah, this was the one that raised the most issues. So question 6 was looking at paths. So here's the graph we've got, and we're asked whether each of these is a path. If it's a path, what's its length? Is it a simple path, and is it a circuit? So A, B, E, C, B. So this goes from A to B to E to C and back to B. Okay, that is a path. It's a path because each edge that we're traveling, begins where the previous edge ended. And so it's a continuous, set of edges. So it definitely is a path. Its length is 4, right? A to B, B to E, E to C, C to B, 4 edges total. Is it a simple path? A simple path travels an edge only once, right? You're not allowed to travel over an edge more than once. So going from A to B and B to A, that would be a simple path. If we also go from A back to B, that's no longer simple. Right? Now we're allowed to cross vertices more than once, and so the go-to example in my head is always the simplified house structure. If you start here, you can go out and go like that. That's an Euler path. All right, so it's a path. Is it a simple path? Yes, but is it a circuit? No. To be a circuit, it would have to be, a path that ends at the same place it began. All right. Question B, A to D, and then back to A, and then back to D, and back to A. So we're basically going around here twice. Okay. It's definitely a path. Right? We got connectivity. It's not a simple, it's a length of 4, right? So the length is the number of edges that you travel across, right? So it's like a distance measure, so that's 4. But it's not simple because we're crossing edges more than once, but it is a circuit. All right, and most people got that it is a circuit. And then questions, parts C and D, they're not paths, so this one goes from A to D, and then from D to B. Well, there's no edge from D to B. So it's not a path, right? So yeah, path is determined by edges, not vertices. All right, so C is not a path and D is not a path. And if it's not a path, you can't talk about its length. If it's not a path, it can't be a simple path. And if it's not a path, it can't be a circuit, because a circuit is a path that starts and ends at the same vertex. So C and D, the answer is just no, 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 no. And then 7 asks, does this contain an Euler path? So an Euler path is a simple path that that travels along each edge, right? So you have to go over each edge exactly once. So we can go from A to B to C and back up to A. That takes care of the top part. We can come down here, and then we can loop around B and back to D, and then we can loop around here to C and back to D. That will have traveled every edge exactly once. So that's an Euler path, but it's not a circuit because we didn't come back to A where we started. And in fact, there's no way to do a circuit. And we talked a little bit last week about how the theorem that we had for Euler paths applies to directed graphs. And it's about looking at the in-degree versus out-degree difference of each node. But you can just kind of experiment with this and find the Euler path pretty simply. And then convincing yourself there's not a circuit might take a little more work. But the punchline is there's no circuit. And then Hamilton circuit, I didn't grade this one, but Hamilton circuit, there is no Hamilton circuit. And it's this vertex here that's going to mess things up, because once we visit here, we can't get out. And if we start here, we can't come back, because we can't travel that edge more than once. All right, so I think people are in good shape on graphs. Any other questions on any of that material? All right, so let's talk a little more about phrase structure grammars. Um, this is what we started talking about on Friday, and you have some homework questions to use to practice your understanding of this. But let's just dig a little deeper into it. I've got about 9 minutes left here. So remember our basic setup. It's a four tuple. We have symbols, we have terminal symbols, we have a start symbol, and we have production rules. And all the magic kind of happens in the production rules. So I'm not going to spend a lot of time writing the formalism of these examples, but let's just try a few examples. So let's suppose our set of symbols is 0, 1, and an A. I might need some more stuff, I'm not sure. Our terminal symbols are 0, 1, and I'll probably stick with these for all of these examples for the next few minutes. Our start symbol is going to be S, so that'll be a symbol also. And I want to look at the production rules. So our production rules are going to be the following. All right, there's a set of production rules. So this is a scribble. So our start symbol can go to the empty string, or it can go to the symbol A. And the symbol A can go to either 0, 1 followed by an A, or it can go to an empty string. So what strings are recognized by this grammar? Well, certainly the empty string, because the empty string is in fact directly derivable from the start symbol. So that's one string recognized. What would be another string that would be recognized by this grammar? Something that we could get to from the start symbol using these production rules. So we can certainly get to A. What can we get to from A? And A is the only other thing we can get to directly from S, right? So what can we get to from A that's comprised just of terminal symbols? So we can get to A, we can get to 0, 1A. What else? Keep going along that line of thought. Because we can get to 0, 1A, but we know that A can also take us to 0, 1A, so yes, 0, 1, 0, 1A. And now we're off and running. Right, all of those things. So you can repeat 0, 1 over and over and over again, but we also have the possibility of A changing into the empty string. So this could take us, well, I mean this A could take us to 0, 1A, or it could take us to lambda. As 0, 1A could take us to 0, 1, 0, 1A, but it could also just take us to 0, 1, where this A was used to derive lambda, the empty string. And this could take us to 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, and so on. So the languages that are, the strings that are recognized by a language, right, must be comprised of terminal symbols only. So they are exactly these things. So this language recognizes any repetition of the string 0, 1, including 0 repetitions. And yeah, since they can go to lambda 0, 1. Terminal symbols are it's a subset of our collection of all symbols. But when we talk about, what is a word recognized by this language, we always mean a word comprised only of these select symbols, these terminal symbols. So these other things like A and S, these are sort of intermediaries. They're temporary variables, if you like. Whereas the terminal symbols are things that we would actually make our word out of. So for example, with English sentences, when you're diagramming a sentence, you might say this is a noun, or this is a verb phrase, or this is an adjective, right? But we wouldn't use the symbol N-O-U-N or, V-E-R-B when we were writing a sentence, right? We have to have letters of the alphabet and punctuation in our sentence. So these are like, temporary things that we can use to help us build up these patterns of terminal symbols. Yeah, basically, that's an interesting way to think of it. S could be like a manufacturer, and T is the product. That's a pretty good analogy. So we can analyze this by basically, trying to apply these production rules in different ways. And sometimes we do this with a tree-like structure. We would start with, S, and say that could be a lambda, or it could be an A. And A could be a 0, 1A, or it could be a lambda, and this A could be a 0, 1A, or a lambda. And if we follow this through, right, we can see, for example, here's 0, 1, 0, 1 followed by an empty string. That's this symbol right there. So the analysis of these is important, right? And I think there's some homework questions that say, what are some words recognized by this? And you can find these in the textbook also. The analysis helps us, get our brains around the idea of how do these production rules work together to produce words that are recognized by the language. But the other piece of this is the synthesis piece. And synthesis is always more challenging than analysis. Right? So in programming, analysis is, looking at a program and understanding why it works. Synthesis is writing the program yourself. In Engineering 250, analysis is here's a circuit, write a truth table for it. Synthesis is here's a truth table, give me a circuit that does this. Right? It's a little harder. And my classic example, physics, analysis is here's a picture, and here's what the forces look like, and here's the equation, and so here's how fast the Ferris wheel is turning at time t, and you can look at that and understand it. Synthesis is coming up with that out of nothing, right? So synthesis of phrase structure grammars is I want a grammar which recognizes the following strings. For example, I want a grammar which recognizes, either 0 followed by a bunch of 1s, followed by a 0. All right, so I want a 0 followed by a succession of 1s followed by a 0. How do I make a phrase structure grammar to recognize this? And so I need to scoot to my meeting, but try this. See if you can figure out, language, symbols, terminal symbols, set of production rules that will recognize, let's say 0, 0, 0, 1, 0, 0, 1, 1, 0, all of those things. And you can do it with a few production rules, but until you get in there and get your hands dirty and start trying to write rules and see what they do, there's no algorithm for coming up with an answer to this question. It's something that you figure out somehow by trial and error, and because our brains are these marvelous things. But it requires you to analyze the rules that you're coming up with to see if they're doing the right thing. So you've got to get some practice with analyzing these grammars first, and then play around with synthesizing them. All right, so my meeting is on Skype, so I'm going to have to close the Skype room. I will see you next time. I'll see you in 224 tomorrow. Most of you are in 224. And check out those videos when you have a chance. That video that I posted. All right. Have a great afternoon. I will see you next time. All right. Bye.